Hello, my name is Uliana Alekseeva, and I'm going to tell you about our activities concerning porting FLEUR onto GPGPU. This is a slide from my previous presentation, and it shows you why we are excited to see the exascale machines coming. We are already able to calculate quite large system with our code, with FLEUR. But with the exascale machines, it will be possible to run high throughput computation, and it will be possible to study how these magnetic structures evolve in time. Let's see how the performance developed since 30 years. If you follow the talks in this workshop, you probably see the picture already for the third time. But let's have a closer look. Here the performance in flops, floating point operations per second, plotted against the years. This middle line, the orange one, this shows you the performance of the top one machine. This point here represents the Fugaku with 400 petaflops. The blue line is the last one machine in the list, number 500. It's interesting to see that already since 2019, there is no machine in the list with performance less than 1 petaflop. The green one is the sum of them. If we consider that, then the exascale era is already here. You maybe have heard about the Moore's law. This states that the number of transistors on a chip will double roughly every 2 years. This is this trend. Since 50 years, we see that this trend is there, but it's not really directly translating into the performance. You see the single thread performance here. Because using more transistors does not directly make your code faster. What makes your code faster is raising the frequency. And we see that frequency also followed this trend, but not then stopped following. The reason for that is that if you increase the frequency, the power dissipation on your chip also will increase, and will increase cubically with the frequency. The power trend you can see here. To give you the feeling of what we are dealing with, Fugaku consumption is 30 megawatt. A wind turbine can produce 3 megawatt. A consumption of a household is about 1 kilowatt. So high performance computing is very costly. You see from this trend here, number of logical cores per socket. You can see here that in the year 2005, people decided, well, if we cannot use these transistors directly for the performance, let's increase the number of cores. You see quite prominent king here. This king, it's so famous, it even has a name. It's called end of free lunch, because before you can write your code, you can wait a couple of years, and with new hardware you can run your code faster. That is not the case anymore. Now, if you want to run faster, you need to roll up your sleeves and start optimizing. Let's have a look on top 8 machines in the list. We see quite a different architecture here, but we also can see that 6 of them has accelerator. And it's interesting to check the power consumption and also to compare, for example, the Fugaku and the Jewel booster. the difference in performance is about 10 times. But the difference in power consumption is about 20. It's actually 17. So it looks like that using accelerator really can give you some advantage. It's really nice to use a GPU in your calculation. So let's check why. Let's try to understand why. And actually, it is a matter of speciality. If we consider two vehicles here, we see that they are both good, but in different kind of strategy, right? If your aim is to transport one person fast, then you might want to use motorcycle. But if you want to transport many, it can be at the end more efficient to use a bus, although the velocity of the bus is not as high as velocity of a motorcycle. And the similar picture is with CPU and GPU. If we take a look at the Intel SKYLAKE chip and zoom in and have a look at the core, the part of the die which is actually do calculation, which is actually do number crunching, is just this. The remaining parts are caches and some control logic. And if we think about why this area is so small, it's because actually these architectures were not for computing. Long time ago, the mainframe computers were specially designed for scientific computing. They were far more performant than commodity computers. But now, the supercomputer is a cluster of servers, and the architecture of these machines are the same as in the machine you will find on your desktop. They are very sophisticated. They do a lot to make your computation fast. They have a lot of interesting features. You have, for example, superscalar pipelines. Pipelines chop your operation like addition or multiplication in smaller parts, which are more simple. That's why you can do per cycle less, and then you can speed up the cycle. Superscalar means you have several of them. On this picture, 2 of them. So if you have independent instructions, you can perform them in parallel. CMD, single instruction, multiple data. You can work with one instruction on a vector of a data which contains, for example, 8 double precision numbers. You have out of order execution. You can shuffle your instruction a bit, but for that you of course need instruction cache. You also need some machinery to transform a complex instruction set to reduced instruction set, which again allows you to speed up the cycle. You have branch prediction. You have memory caches. Why do you need memory caches? Because fetching data from the main memory is very slow. So you start, you do the data prefetching. You start fetching the data from the memory, let's say 100 cycles before you really need them. But of course, then to store them, you need memory caches. Now let's compare it with the GPU. This one now is rather a sketch, but it will give you an idea. On the left, it is the CPU. You have large cache, you have large, complicated, sophisticated control logic, and you have a few execution units, which also are quite sophisticated and powerful. On the GPU, the caches are small and control logic are small. That means you as a programmer need to take more care about what you are doing. But you have a lot more of execution units, though they are rather simple. They cannot do such complicated things that execution units on the CPU. I also have some numbers here to compare for Intel Skylake and NVIDIA Ampere. It is not really fair to compare cores on the CPU and cores on the GPU because they have rather different machinery. What cores on the CPU can do rather corresponds to the streaming multiprocessors on the GPU. We have 128 here and 24 cores on here. We also can compare memory. Memory on the GPU is usually smaller, but much, much faster. You see here 1.5 terabytes per second. But CPU is accelerator, so you need a host. We usually have CPU as a host and GPU as a device. And we connect them by PCI bus. And this is usually a bottleneck because this number is not high. You can transport data with bandwidth about 32 gigabytes per second. That's not much. That's why you want to hide this copying data. This usually happens in this way. You start two streams on your GPU, and while one stream is doing computation, the other one is copying that data for the next computation. So when we summarize, CPU optimized for low latency. It has large main memory. You can have a high clock rate. It has large caches, and the execution units are quite powerful and sophisticated. But the memory bandwidth is low. If the data is not in the cache, these cache misses are costly, and since the clock rate are high, the performance per watt is rather low. On the other hand, GPU are optimized for high throughput. The main memory have quite a high bandwidth, and these devices are latency tolerant. You have much more compute resources, and you have high performance per watt. But memory is limited. The performance of one core is rather low because it's very simple entity, and GPU is an extension card. If you want to program GPU, you have many possibilities, but as usual, if you want it easy, it's not very flexible. You can use libraries. Here, the motto is programming GPU is very easy, just don't do it. If you want more flexible solution, but still portable, you might consider using directive, telling the compiler what to put where and how exactly to calculate things. And if you want to be really in control of what you're doing, you might consider use the programming languages. In FLEUR, we have interfaces to cuBLAS, ELPA, and Magma to these libraries. We also use OpenACC for the remaining parts of the code. We used to have CUDA Fortran, but this seems to come out of fashion for the domain scientist nowadays. This is a reminder how the algorithm of FLEUR looks like. These parts are very heavy because they scale cubically with the system size. So metric setup, diagonalization, and new charge, these are the parts which we want to port onto GPU. And this is indeed the case. Matrix setup and the most relevant parts of charge density generation are ported onto GPU using OpenACC. And we also have interfaces to Magma, ELPA, and cuBLAS for diagonalization. We also have an example here. This is not a very large system. It has only 64 agents. And we compare here the execution on an Intel node with the execution on an NVIDIA Pascal card. This is the comparison. And it shows that it works. When system grows, the gain in performance will be more prominent, and it is clearly the ongoing work. You also can see our problem here, that the parts which left on the CPU becomes much more slower. This reflects the difference between Intel compiler and PGI compiler. This is the status of porting FLEUR. The most computationally relevant parts are ported to the FLEUR. Since our code is Fortran code and we use OpenSCC, we don't have much choice in compilers. We have to use PGI compiler, which is now called NVIDIA HPC compiler. We have MPI parallelization, so the multi-node version is available, and we can use multiple GPU per node if we start one MPI process per GPU. The most problematic part is the diagonalization. We have an interface to Magma, and this works well, but Magma is a LAPACK-like library, and it cannot be spread over several MPI processes. So the parallelism here is limited to the K-point parallelism on MPI level. We also have interface to ELPA. ELPA should enable multi-GPU, but this is a bit of work of the development, so maybe later it will be more performant. If you want to try this, if you want to play with it, you need to configure. You need to compile the code specially for GPU, and for doing that, you need to use a special flag in the configure script. This is the summary of my talk. So exascale computing will be fascinating. We will do a very interesting science when these machines arrive, and probably these machines will contain GPU. GPU has a very different architecture, and it's a bit of a challenge to program them. And since FLEUR is such a large and complex code, we depend very much on libraries and compilers from other parties. But we have put a lot of work in this, and the code is mostly ported. Thank you very much.